continue and discuss more about traffic signals. Okay, and I don't think I showed you this slide yesterday, which is about sight distance for a signal depending upon the 85th percentile speed. So if you want to know how much sight distance should be provided for a signal, it depends upon the 85th percentile speed of the road. Okay, and so you go there to that highway and you do the spot speed study, and you find out the 85th percentile, and then on the basis of that you should know at how much distance the signal should be visible. And percentile basically means the highest value for a particular proportion of drivers. So when I say 85th percentile is 20 miles per hour, that means 85% of drivers on that road were driving at 20 or less than 20. Okay, which is a very low value. Okay, moving on to some other terminologies related to signal. I'll start with the one which we have already done, and that is cycle. What is a cycle? We have discussed it when we were discussing a delay and other things as well. We have discussed other topics as well. So what is a signal cycle? What do we mean by a signal cycle? Tell me.
Doctor, is the time from the red to the next red.
Thank you. Yes.
Yeah.
Time from red to red. Yeah. Okay. So we know about cycle, and the time which is taken by the signal to complete the cycle, the number of seconds, are known as cycle length. Okay. And then we have the term interval. What is an interval? Interval is the interval is part of the cycle where signal indication remains the same. Okay, so signal became green and it remained green for 20 seconds. So this 20 second is one interval. Okay, and then after green it became yellow for 3 seconds. So those 3 seconds are the next interval. Okay, and so on and so forth. So whenever signal shows a particular indication, the amount of time for which that indication is on, that is one interval. Okay, and then obviously depending upon the type of light which the signal is showing in the interval, we can have different types of intervals. We can have yellow interval, which is also known as change interval. Okay, yellow or change interval means the same thing. We also have all red interval, okay, which is known as clearance interval. Okay, what happens during clearance interval? All directions are having red time. All directions are having that time. Now, what's the reason for that? The reason is to account for the risky, or the nice term is brave drivers who try to pass the intersection in the last half a second of yellow, right? So when the signal becomes red in their direction, they are already in the intersection. They have crossed the stop line. So as traffic engineer, we are very smart people, so we know about these people, we know about these drivers. So we make sure that no other direction receives green immediately or even yellow immediately. Okay, so there will be a couple of seconds for this driver to clear the intersection, and this is known as clearance interval. So during clearance interval, all directions have red. Okay, and this is for the drivers to clear the intersection who have already passed the stop line. So now they cannot stop, they should clear. And then we have green interval, yellow interval, and so on, red interval, and so on. Then we have the next term, which is a phase. A phase is the amount of time given for any given to the flow in any particular movement, for any particular movement. The total time given for the flow of any movement. Okay, and it includes 3 things: green time, yellow time, and all red time. Okay, so during these 3 times, no other movement will be allowed. The next movement will have its yellow or green once the phase has finished for this particular movement. Okay, so phase is the total time during which a movement is allowed to go. Okay, and it includes green, yellow, and all red time. And obviously, as I said, after all red time, any other movement can begin. Okay, so This is one phase. Signal can be operated in 3 ways. Okay, same signal can be operated in 3 different ways: pre-timed, semi-actuated, fully actuated. Pre-timed means the signal is not connected with any sensors on the road. So signal is pre-planned, pre-programmed, and its timing will not change according to real-time traffic. So you already calculate the timings of the signal and you program the signal according to the timings which you have calculated, and now it is not connected to any sensor on the road. So if the actual traffic changes because of any reason, the signal will operate according to your programmed timings. Okay, it will not change. Now, as traffic engineers, again, we are smart people, so we know that traffic does not remain same throughout the day. Okay, in the morning, one direction may have more traffic than the other direction. In the evening, it may become reverse, and there are some hours of the day where traffic is low in all directions. Okay, so even with pre-timed signals, we prepare and program 3 different timing plans, 3 sets of timings for the signal. One for AM peak hour, one for PM peak hour, and one for off peak hours. Okay, AM means for traffic in the morning, PM means traffic in the evening, heavy traffic in the evening, and off peak means for the rest of the times of the day. Okay, and you install the signal and you program the signal in such a way that for the first for the few hours of the evening, few hours of the morning, it will work according to AM peak timing, and few hours of the evening it will work according to PM peak timing. In the rest of the hours of the day, it will work according to off-peak timings. And as I said, the timings will not change unless you come and change the timing. Okay, it will not change. This is why we call it pre-timed, because you are programming the signal in advance, and it will not change unless you change it. Then we have fully actuated and semi-actuated. Now we have used this term actuated or actuation earlier as well when we were discussing the topic of pneumatic road tubes. So actuated means connected with a sensor. Actuated means connected with a sensor. So a semi-actuated signal is operated when you have a minor highway crossing a major highway, a minor highway crossing a major highway, okay, or minor street crossing a major highway. Okay. Now, semi-actuated means one of these 2 highways will have a sensor, either the minor or the major. Which one you will tell me. But semi-actuated signal operates in such a way that one of the highways will keep on having red time until the car comes on that highway. Only then it will become green. Otherwise, the other highway will keep on having green time. Okay, so a signal is continuously red for one of the highways until and unless a car comes from that side, and then the signal will become green for it and red for the other side. Okay, now my question to you is which direction should have the sensor? Yeah, the minor should have the sensor. Yes, Suzanne, correct, you are right. The minor highway should have the sensor because the minor highway will have less traffic and there will be many there will be a heavy proportion of the day during which there may be no traffic on that street coming from that street. Okay, so obviously in that case the main highway will remain green. Okay, so the minor highway has a sensor, and that sensor will indicate to the signal that there's a vehicle or not. Unless the signal gets an indication from that sensor, it will remain green for the major highway. Okay, so this is the operation of semi-actuated. In fully actuated signal, we have sensors on all directions. So it is used where 2 major highways are crossing each other, 2 major highways. Okay, even for 2 minor highways, you can work without sensors. If 2 major highways are crossing each other, so you will have heavy volumes coming from all directions in different times. So then you can use fully actuated signal. So obviously in fully actuated signal, timings for all movements can change, all phases can change. Okay, and if you change all phases, then the complete cycle length can change as well. So if you have heavy volume coming from all directions and you try to provide more green time to everybody, obviously the complete cycle length will be increased. Okay. Another thing which can change in fully actuated is the phasing, the order of phasing, the sequence of phasing. Okay, so for example, in one cycle, you have the phasing east, then west, then north, then south. Okay, this is the order: east, west, north, south in one cycle. In the next cycle, the sensor on the north side indicates more signal. It detects more vehicles. Okay, so after east, the north side may receive the next green time, and the west and south will receive after it. Okay, so in fully actuated signal, depending upon the volume, even the sequence of phasing can change as well. Okay. Then something which I mentioned yesterday, signals on a major highway which is crossed by multiple minor streets can be coordinated so that vehicles which are moving through the main highway can continue moving without stopping on each and every signal. So you go from signal 1 to signal 2. By the time you reach a signal 2, it is already green for you and you continue moving. Okay, so this is what we call a signal coordination, and this is applied where signals are close to each other. Where signals are close to each other, if signals are far from each other, so coordination cannot be applied. Okay, how close? How much close? They have given us a limiting value which is 0.5 miles. So 0.5 miles is around 800 meters. Okay, so if signals are less than 800 meters to each other, you can apply signal coordination there on the major street. Minor street, drivers may still have to stop. Examples of semi-actuated signal, if you come to traffic directorate driving school, the side street of the driving school is coming on Sheikh Zayed Highway. So they have installed a signal this year on that street at the start of this year, and that signal is semi-actuated. So unless somebody is coming from the side street of the driving school, the Sheikh Zayed Highway signal will remain green. So that is an example of semi-actuated. Fully actuated, look at any signal on Sheikh Zayed Highway, Sheikh Salman Highway, or any other main highway. The major intersections are fully actuated. Okay. Signal coordination, I think I mentioned it earlier as well. The highway, Wadi Al-Sail Highway, okay, signals on that, and Nasan Highway, they are coordinated. Okay. So the difference of timing between the coordinated signals, difference of green timing for the coordinated signals on the main street is what we call as offset. The difference of timing on the main street for a coordinated signal is known as offset. So if one signal is green and the next one becomes green after 10 seconds, so this 10 seconds is offset of the coordinated signal. For coordinated signal, it is important that the cycle length is common for all the signals. The cycle length is common for all the signals. If you don't have a common cycle length for all the signals, coordination cannot be achieved. Okay, so all coordinated signals must have the same cycle length. Okay, then we come to the concept of saturation headwind, saturation flow rate. Now we have discussed flow rate a number of times. It was in both the exams. It has been covered in many topics. So I hope you remember it. Okay, and I will ask a question about it. But presently my question is, what is a headway? What is a headway? We covered it in lecture 3 slides. What is a headway? If I say headway between the vehicles this much, what do I mean?
Doctor, it's the time needed for the. I guess it's related to the time.
Okay, thank you, Zan. Who else can complete this answer?
The time required for 2 vehicles to pass one point, one specified point.
Yes, yes. You Googled it?
No, Doctor, I remember.
Okay, good memory. Okay, Raneem and Mariam, yes. Again, like I mentioned, is time, not distance, time. Okay, both of you are correct, but in terms of time, not distance. Okay, spacing is distance between car and another car, but headway is time between one car and the other car. Okay, to cross the same point. Okay, so headway is the time interval between two consecutive cars. Now, what is saturation headway then? Saturation headway is the minimum headway at which the cars will move through the intersection. This is a simple definition, just to make you understand. And you can see the definition of the book written here. Okay, the simple definition is the minimum headway at which the cars can pass through the intersection. That is saturation headway. And according to the book, they are saying average headway achieved by a saturated, stable moving queue of vehicles through the signal. Okay, so saturated means, again, referring to minimum. When you have something saturated, that means the spacing or the interval between them is minimum. Okay, so saturated is referring to that it will be a minimum value of headway, and stable means it is continuous moving of vehicles. Okay, so minimum headway which you can achieve, or saturated headway which you can achieve for vehicles which are passing through the intersection continuously. Okay, that is saturation headway. And again, in lecture 3 sites, we discussed that the relationship between headway and flow rate is this one, inverse, where 3600 is the conversion from seconds to hours. Okay, so if you know saturation headway, you can calculate saturation flow rate as well, which is the inverse of saturation headway. Okay, so S is saturation flow rate and H is saturation headway. When you do the inverse of one, you get the other one, which is the basic relationship of headway and flow rate. So if you take the inverse of saturation headway, you get saturation flow rate. Okay. Now, saturation flow rate is a hypothetical, theoretical, or imaginary value. Why? You can only achieve saturation flow rate if signal remains green for a direction for 1 hour continuously. If you have 1 hour continuous green, only then you can achieve flow rate equal to saturation flow rate. So obviously now you can imagine we cannot design a signal which will remain green for 1 hour. Okay, people will think you are stupid and they will throw you in a mental hospital. Okay, so saturation headway is an imaginary value. Okay, it's a hypothetical value and it can be calculated by taking the inverse of saturation headway. Now the point is, how do I find out saturation headway? For that, there's an experiment. When I was in Karachi, I was teaching in Pakistan. In our lab, we used to have this experiment. Okay, how to calculate saturation flow rate? The students used to go to the signal and they used to calculate saturation headway. The procedure is, when the signal becomes green, you will start noting down the headway between the vehicles when they are crossing the stop line. So from the first to the second vehicle, how much time was taken? From the second to the third vehicle, how much time was taken? And so on and so forth. Okay, to cross the stop line. Now what happened? And according to traffic engineers, according to previous knowledge, we know that from third or fourth vehicle onwards, the headway becomes equal to saturation headway value. So the first 2, 3, or 4 vehicles, or the first 2 or 3 vehicles do not have a value equal to saturation headway between them. They are usually higher. The headway between the first 2, 3 vehicles in the queue is usually higher than the saturation value. Okay, so if you want to observe saturation headway, you will take the values from the third or the fourth vehicle of the queue onwards. Okay, how many vehicles you have in the queue? Okay, so you record the time interval between them and you will take the average. That will become saturation headway from third, fourth vehicle onwards. Why first 2, 3 vehicles to take more time? The reason is when the signal became green or the yellow, the driver will take some time to get prepared to move, putting the phone away, changing the gear, or whatever he was doing, talking to some guy or something. So he will take some time to get prepared, and when he will reach the stop line, his speed will be lower because he had less time to accelerate. The people, the drivers who were farther down the queue, they had more time to prepare because when the signal became green, they already had 3 or 4 vehicles in front of them. So when their turn came to move, they were already prepared. They already took the time in which the other drivers were moving and they were well prepared. And some of them are too restless and they will start honking you. Okay. So, those guys, the third, fourth vehicle onwards, they had more time to prepare and they had more time to accelerate as well when they reached the stop line. So because of this, their headway becomes minimal. Okay, and because of this, the headway for the first 3-4 vehicles is higher than the saturation headway value. Okay, so it usually follows this trend. On the x-axis you have number of cars, on the y-axis you have headway. For the first car it is higher, second car lower, third car lower. It will keep on getting lower until for the third or fourth vehicle it becomes equal to the saturation headway value. Okay, so then you can see now it becomes constant. This is saturation headway. And the extra headway taken by the first 3-4 vehicles in the queue is known as startup lost time, denoted by L1. What is L1? The extra headway taken by the first 3-4 vehicles, extra headway compared to the saturation headway value taken by the first 3-4 vehicles in the queue. This is startup lost time. Okay. Extra headway taken by the first 3-4 vehicles in the queue compared to the saturation headway. Okay, this is startup lost time. So delta is the difference between the headway of the vehicle and the saturation value. So you have 3-4 values of delta, you add all of them, you will get startup lost time. In one phase, now remember phase means the complete time given for a movement. In one phase you have 2 types of lost times. So let's say the total lost time in one phase is TL. So TL comprises of 2 things, 2 items. One is the startup lost time, L1, we already discussed it. The other one is L2, which is the clearance lost time. So clearance lost time again was the time when all signals were red. Okay, so this is also part of lost time. So one phase has 2 types of lost time, clearance and startup. Okay, clearance means all red and startup is the extra headways. Now there are 2 types of green times. For any phase there can be 2 types of green times. One is actual green time, the other one is effective green time. Actual green time is the one when the signal was actually showing the green light, and we represent it with capital G. So capital G is the actual green time when the signal was showing green light. What is effective green time? The amount of phase time during which cars were moving at saturation headway value. Okay, the amount of phase time during which the interval between the moving vehicles was equal to h, saturation headway. That is effective green time. Okay, how can we calculate effective green time? Effective green time can be calculated using this equation, which is G plus capital Y minus TL. Okay, now what is capital G? Actual green time. Capital Y. Now keep one thing in mind. We will use capital Y and a small y both. Capital Y means green plus, yellow plus all red. Capital Y means yellow plus all red. Okay, and a small y means only yellow. Okay, so this is yellow plus all red, and TL is lost time, total lost time on one phase. We already discussed it. Okay, so green plus capital Y gives you total time of the phase. Okay, green plus yellow plus all red, total time of one phase minus lost time. So that will become the effective green time. Simple. Total time minus effective, total time minus lost time becomes effective green time. Okay, and whatever is not effective green is also known as effective red. Okay, so one phase can have effective green and effective red. Whatever is not effective green is effective red. Okay. Now, using the things which we have discussed up till now, we can do this example where we will be calculating the capacity of one movement, capacity of one phase of the signal. Okay, and we will do it using two different approaches. Okay, now what is given here? The total cycle length, capital C, 60 seconds. Actual green time of one movement is given, one phase is given. Okay, 27 seconds. Yellow plus all red, you can see capital Y, 4 seconds. Saturation headway, 2.4 seconds per vehicle. The startup loss time, 2 seconds. Clearance loss time, 2 seconds. We want to find out the capacity per lane for this movement. Now keep one thing in mind. In this example, we will be using saturation headway to calculate capacity. So whenever you use headway to calculate capacity or flow rate, it is by default per lane. Okay, using headway to calculate capacity and flow rate is by default per lane. Okay, so you will calculate per lane. Okay, so don't worry about number of lanes here, although you have to calculate per lane, but it will be taken care of during the calculation. Okay, first of all, let us calculate the effective green time. Okay, effective green time equals actual green time, which is 27 seconds, plus yellow and all red, which is given as 4 seconds. Okay, minus total loss time. Total loss time is clearance plus startup, both are given as 2 seconds. Okay, so now tell me the effective green time here, how much it is. Plus 4 minus 4, 27 seconds, right? Effective green time is 27 seconds. Now this is effective green time for this phase in one cycle. Okay, effective green time for this phase in one cycle. Okay, you have any question? Yeah, simple calculation, right? Okay, now I want to calculate for the first approach for solving this problem. I need effective green time in the entire hour. Okay, this is the effective green time in one cycle. I want the effective green time in the whole hour. So I will calculate number of cycles in 1 hour. Number of cycles in 1 hour. So in 1 hour, I have 3600 seconds. And one cycle is 60 seconds in this example. Okay, so divide by 60. Now keep one thing in mind, cycle length can change. In every example, in every problem, it cannot be 60 seconds. Okay, some of you did this in the exam as well. God knows how do you remember these values. I'm amazed that you remember the value of the volume which you took in the class example, but you don't remember the procedure of solving it. Okay, but some of you did it. You remembered the values from the class example and you use it in the example of the exam. Don't do it. Cycle length can change. In this example, it is given as 60 seconds, so I'm dividing by 60. Okay, so 3600 seconds in 1 hour and 60 seconds of one cycle. So this will give me number of cycles in 1 hour. So how much is it?
It will be 60, Doctor.
60 cycles in 1 hour. Okay, and in each cycle, I have 27 seconds of green time. Okay, so how much green time in 1 hour? Effective green time. Okay, I'm trying to use capital G, a small g here. So how much effective green time can I have in the whole hour? 27 of one cycle multiplied by the number of cycles. How much is it?
1620.
In 20 seconds. Okay, This is the effective green time in the entire hour. Now remember, I defined effective green time as the time during which interval between the vehicles is equal to h, saturation headway. Okay, so if I want to calculate how many vehicles can pass in 16-20 seconds, I know the interval between the vehicles, which is 2.4 seconds, I guess. Okay, so during these 16-20 seconds, vehicles are passing with an interval of 2.4 seconds. So how many vehicles can pass in 60-20 seconds? That is the capacity. So 16-20. How much is it?
675.
675 vehicles per hour per lane. Okay, so what do I do here? First of all, I calculated effective green time for one cycle. Then I calculated how many cycles I can have in 1 hour. Then I multiplied these two to calculate total effective green time in the entire hour. Then I divided by the interval at which cars move during effective green time, that is saturation headway, to get how many cars can move, which is 675. This is one approach of solving this example. Another approach is by using the saturation headway. Saturation flow rate. By using the saturation flow rate. So I told you saturation flow rate is the inverse of saturation headway. Okay, so 3600 for the conversion divided by 2.4, the saturation headway. How much is the saturation flow rate here?
Uh, 1500, Doctor.
1500 vehicles per hour per lane again, because again we are using a headway. Now, as I told you, you may achieve flow rate equal to S if the entire cycle length was effective green, right? This is what I said, that if the entire cycle length was effective green, so for the whole hour you will have green, effective green, and then the flow rate can be equal to S. But actually this is not the case. So how much cycle length is effective green? 27 seconds. Out of 60, 27 seconds is effective green. Okay, so if all 60 seconds were effective green, capacity will be equal to S. But since I have a proportion of cycle length as effective green, so capacity will be equal to the same proportion of saturation flow rate. Okay, so if G by C, let me write it here. If G by C was 1, then capacity will be equal to saturation flow rate, meaning the whole cycle is effective green. Okay, but I have a portion of cycle which is effective green, so I will have a portion of saturation flow rate as the capacity. So again, this is 1500 into 27 seconds effective green divided by the cycle length 60 seconds. Okay, 60 seconds of cycle length, capital C, should be equal to 675 vehicles per hour per lane. Okay, you should be getting the same answer because we are still talking about the same signal, right? Same approach, same signal. So both approaches should give you the same answer. Okay, so in one approach, I use the total time of the hour divided by saturation headway to calculate the capacity. In the second approach, I calculated saturation flow rate and then I multiplied with the proportion of hour, which is, or the proportion of cycle length, which is effective green. Both cases will get the same answer. Okay, do we have any questions right now? Do you guys have any questions? Because the next calculation is related to this example. If you understand this example, the next equation will be easier. Any questions right now? Is it clear? Okay. Now we have just calculated capacity of one movement, one phase. Okay. How about calculating the capacity of the entire intersection? Combination of all phases, right? Combination of all movements. How about that? To calculate the capacity of the entire intersection, you can do the same calculation for every approach. Okay, for every approach, calculate, the capacity, and then you add them together. This can be done, okay, but obviously it will take more time. Why don't we develop one equation which will give us the entire capacity with one with one set of calculation. So to do that, we will be using these terms. What are these terms? The first term is lost time per cycle. Now lost time in one phase was denoted by TL, and you multiply with n. What is n? Number of phases in one cycle. So in one phase I have lost time equal to TL. So total lost time in the whole cycle will be number of phases into TL. Okay. Then lost time in the entire hour. In one cycle I have lost time equal to L. If I multiply with the number of cycles in the hour, I will get lost time of the whole hour, like we did in the previous example, right? The first approach. This is what we did with the effective green time. Okay, we calculate effective green time for one, and then we multiply the number of cycles. So L into 3600 upon C. What is 3600 upon C? A number of cycles in 1 hour. 3600 seconds of 1 hour divided by capital C, which is number of seconds in one cycle. Okay, so this will give me LH, total lost time in 1 hour. Lost time in one cycle was L. LH is total lost time in 1 hour. Then whatever is not lost time is effective green for at least one of the approaches, right? Okay, whenever you don't have a lost time, at least one of the phases will have effective green. Okay, so if you want total effective green for the entire signal, you will do 3600, the total time of 1 hour, minus LH, which was the lost time in 1 hour. So this will give you total effective green time in 1 hour. Okay, total time minus lost time. Simple. Now during effective green, we already know the vehicles move at a headway of h, at an interval of h. So you want volume for the entire intersection. This will be effective green time upon h, like we did in the previous example. This is the same approach of the first method. Okay, so TG, the total lost time of 1 hour, divided by h, which is the interval at which vehicles move during TG. So this will give you the number of vehicles which can move through the entire intersection in 1 hour. This is what the entire intersection. So VC is the capacity of the entire intersection. Now if you want the value of VC, then I can reinsert the values of all the parameters in the equation of VC. Okay, so TG can be replaced with this, LH can be replaced with this, and L can be replaced with this. Okay, so if you put all the values of the parameters, whichever is available in the equation of VC, the final equation of VC will be this one. How did I get this equation? I started from here, put the value of TG, then I put the value of LH, then L, then here. LH, and then the value of L. Okay, so in the equation of TG, I have combined all these other equations. So the final equation is this: H is saturation headway, N is number of phases, TL is lost time per phase, capital C is the cycle length. Okay, now in this equation, if you keep everything constant, everything I mean, if you keep TL and H constant, lost time and headway, if you keep them constant and you just try different values of N and C, then you will be getting curves like these. Okay, the values can be used to plot curves like these. Okay, so you can see on the x-axis cycle length, on the y-axis VC, and each curve is for a different value of N. Now on these curves, you can see two trends. The first trend is when I increase the cycle length, capacity increases. When I increase the cycle length, capacity increases. Why? More cycle length means more green time for every movement. More cycle length means more green time for every movement. So capacity will increase. More green time, capacity will increase. And when I decrease the number of phases, when I increase the number of phases, capacity is decreasing. When I increase the number of phases, capacity is increasing. Capacity is decreasing. Okay, so inversely proportional. Increase number of phases, capacity decreases. What can be the reason for that? The reason is with each phase you are increasing its lost time. You are introducing its lost time. Each phase has its own lost time. So when you were having 2 phases, lost time was multiplied by 2. When you had 3 phases, lost time is multiplied by 3. So you are increasing the lost time with every phase. Okay. So from this graph, we can understand that we should try to maximize the cycle length and minimize the number of phases to have maximum capacity, right? Maximum cycle length and minimum number of phases will give you maximum capacity, right? This combination will give you maximum capacity. Minimum number of phases for a signal can be 2. 2, because 1 means what? 1 means no signal, right? Everybody has green. 1 phase means everybody has green at the same time, which is not a signal. Even with 2 phases, it is not possible on most of the locations. 2 phases means what? You have 4 directions. Every two directions are going in the same phase. So you have 1 phase for 2 directions and the other phase for the other 2 directions. Okay, this is the combination for 2 phases, right? And now you can imagine if I allow 2 directions to move at the same time, it will be dangerous. Okay, so decreasing the number of phases may not be possible because of the safety concerns. Decreasing number of phases means you have to allow more than 1 movement in the same phase, which is dangerous. Okay, so you have to take care of that fact. The other thing is, what will happen if I keep on increasing the cycle length? If you keep on increasing the cycle length, basically you are increasing the waiting time for the driver who has stopped on red. Why? Let's say the cycle length is 60 seconds. I am a driver. When I arrived at the signal became red, I stopped. I know, even if I don't know, I have an idea. Okay, drivers have an idea that which signals take longer, which signals take less time. So as a driver, I have an idea that this signal will become green in the next 60 seconds. And as traffic engineer, we know the reason is that the cycle length is 60 seconds. Okay, so the maximum waiting time for me is 60 seconds. Let's say you increase the cycle length to 120. What will happen? The maximum waiting time can go up to now 120 seconds. If I arrived at red time, I may get the green after 120 seconds, which is 2 minutes. Okay, so increasing the cycle length can be frustrating for the drivers. Okay, because they know now they are stuck here for 2 or 3 minutes. Okay, 2 or 3 minutes is a lot of time for drivers who are going somewhere. And even if you are not going somewhere, just waiting is not good. Okay, so minimize the number of phases, keeping in mind the safety, and maximize the cycle length, keeping in mind that it should not be impractical with regards to the driver. Nobody wants to wait for 10 minutes, right? Now, so this is the equation we developed, right? Now, I can rearrange this equation to calculate the cycle length. So I put C on the left-hand side, everything else on the right-hand side. So this is the equation for minimum cycle length of a signal, for designing minimum cycle length of a signal. Okay, so I've just rearranged the terms, C on one side and other terms on the right-hand side. Okay, so this is the minimum cycle length you should have for allowing VC volume equal to VC to pass in the peak hour. Okay. Now, if you remember what we have been doing, we never calculate capacity in terms of volume. Capacity is always calculated in terms of flow rate. How can I convert volume to flow rate? Tell me. If I give you volume and ask you to calculate flow rate, what would you do? How can we convert volume to flow rate? No. This is conversion for flow and flow rate. This is a conversion for flow and flow rate, not volume. We use a factor. Let me make it easy. No. We use a factor. What is the name of that factor which is used for converting flow to flow rate? Oh, sorry, flow rate to volume. Flow rate to volume. Peak hour factor. Thank you, Mariam. Peak hour factor. Okay. So if I give you volume, divide by peak hour factor, it will convert to flow rate. Okay. We have done it in the last example of the two-lane highways as well, and even before that for all other highways. We did it. Okay. So this is volume, and I want the capacity in flow rate. So VC should be divided by peak hour factor. Okay. Another thing which we should do is, and something which we have discussed for freeways and multi highways as well, VC is the peak hour volume. Okay. In the peak hour, I don't want the capacity to be exactly equal to the actual volume. Okay, because then there is no margin of safety, right? There is no safety factor of safety there. If both are equal, then there is no factor of safety. Okay, maybe you made some calculations, you made some calculation error, and the actual volume is more than what you have calculated. There is no margin of safety. Or maybe traffic increased because of an event. Again, it will cause a traffic jam. Okay, so we want to keep a margin of safety. For that, we will divide VC with another factor, which is V by C ratio. V by C ratio. What is V by C ratio? Volume to capacity ratio. Volume to capacity ratio. Okay, so when V by C is 1, that means peak hour volume equals capacity of the intersection. So V by C should be less than 1. Capacity should be higher, volume should be lower, so V by C ratio should be less than 1. And the recommended range of V by C is this one. Okay, so when you divide or when you put values of peak hour factor and V by C ratio in the equation of cycle length, it is now called as desirable cycle length. So without these factors, we have minimum cycle length, which may work, may not work, but with these factors, we have desirable cycle length, the preferable value of cycle length. Okay, and this is the one which we should use. Okay, let us look at a very quick and a small example. Three-phase signal is given, loss time is given, headway is given, peak hour factor, VC, and they want us to calculate desirable cycle length using different values of V by C ratio. Okay, so they want us to observe the effect of V by C ratio on the cycle length. Okay, so what are the things which are given? TL is given, 3 seconds per phase. No, we have 3 phases, sorry. N is 3. TL is 4 seconds per phase. Saturation headway 2.2 seconds per vehicle. Peak hour factor 0.9. The peak hour volume 100 vehicles per hour. And V by C ratio, we will try these values. Okay, start from 0.8, then you use 0.85, then 0.9, then you use 0.95, and then you will use 1. Okay, so C desirable equals, I have the equation here, N into TL, so 3 into 4 divided by 1 minus VC upon all these things. So VC is 1200 divided by 3600 upon H, which is 2.2, by peak hour factor, which is 0.9, multiplied by V by C ratio. Like I said, I'll start with 0.8. Yeah, tell me the value. Yeah, anyone? Cycle length?
Doctor, can it be negative?
Yes, tell me the value.
Oh, it's minus 6480. 648, sorry.
Yeah. Okay, now
0.8, yeah.
now just replace 0.8 with 0.85 and recalculate the value.
$289.89, doctor.
289.9. Okay.
The next one is 126.78.
Okay.
And then 84.33.
Okay.
And then 64.8.
64.8. Okay. Normally we round off the cycle lengths, but for the time being, just keep it as it is. You can see two important points here. First of all, when you increase the V by C ratio, cycle length decreases. Okay. Why? Because when you increase the V by C ratio, you are making capacity closer to the volume. Okay, so you are actually decreasing the capacity. Okay, so then you need less cycle length. Okay, increasing V by C ratio means capacity is becoming closer to the volume, so that means it is decreasing. So you need less cycle length for that case. Okay, and then you see a negative value. Negative value means that the combination of values cannot, which you have used to calculate this negative answer, is not practical. Okay, so the combination of values which gave you a negative answer, you have to change some of these values. Like in this example, we changed the V by C ratio. We will do another example in the next lecture where we will see how we can change something else as well. Okay, but negative means discard this value. Don't use it. Okay, don't take absolute. Don't ignore the negative sign. Change some values in the equation so that negative becomes positive. Okay, so negative answer is an indication that the combination of values is not valid, is not possible. Okay, so any questions? Any questions, clarifications?
Thank you very much, Doctor.
Okay, you're welcome. So see you guys after the National Day next week. Have a nice long break. Enjoy yourself. And to make you enjoy, I will inshallah upload your grades soon. They are prepared. I just need to type them. Okay, so it will be a nice gift.
Doctor, if it was good marks, yani.
Yeah, but at least some of it. Okay. Okay. See you next week, inshallah. Assalamu alaikum.